hopefully it works. Okay, great. So can you see my slides?
Yes.
Yes.
Perfect.
Okay, great. So thank you for coming. Let me see. Yes. Okay, so thank you for coming. So this lecture is going to be something, it's going to be about a specific implementation actually of a method, which is an internal replica exchange implemented in the combination of GROMACS and PLUMED. So we will use GROMACS during the exercises. So this is something that is very specific for GROMACS. So it's not available in other codes, even though there are similar implementations of the same method probably available in other codes. I'm at least sure that it's possible to do this with Amber. So maybe something that you will learn would be useful also in other contexts. So an important thing is that I will assume that you are already kind of familiar with the GROMACS and with PLUMED to some extent, and also encourage you to have a look at Masterclass 21.5 if you didn't already, where last year we discussed about simulations with multiple replicas with PLUMED. So, okay, first, enhanced sampling. So the goal of today is to give you an introduction to the method. I don't want to give a general introduction to enhanced sampling methods, but I like to quote this recent review from Jerome Menin, which I think it's very nice because it conveys the message that choosing the right enhanced sampling method is kind of a mess because there are so many. So, but this is a useful guide through the zoology of methods that have been developed in the past 20 years. And to put on the map what we're going to discuss today, it's exactly this, which is replica exchange methods. So it's something which preserves the original distribution, and one uses transitions to other ensembles, and then these ensembles are simulated in parallel. Okay, good. Now, replica exchange methods can be used for many purposes. So this is a slide that I stole from my previous presentation for Masterclass 21.5. So there can be many guiding principles to design the ladder of replicas. So in some cases, you want to just bridge your system from state A to a state B, or you could even have like a graph of different states connected. In this case, so let's say you have at the one end of the ladder, you have a system of interest. At the other end of the ladder, you have another system of interest, and you want to convert from one to the other, or a state of interest and another state of interest. There are it's also possible to use replica exchange for something which is tempering. In this case, the system of interest is basically only one, so like this one. But you include other replicas, making some changes so that the dynamics is more ergodic. A typical example is increasing the temperature. Or you could have some just mixed simulations where, for instance, every simulation is biasing, I don't know, is doing metadynamics on a different collective variable and so on. That's the case, for instance, of bias exchange metadynamics. So in case of bridging between two states, it's recommended to do replica exchange. And we discussed that, I think, in the previous masterclass, but it's not technically compulsory. Whereas in these two other cases, basically you have that each simulation is exploiting the fact that other simulations are more ergodic. So it basically makes no sense to use these methods without replica exchange. And then if you use replica exchanges, typically when you bridge between two states, you are interested in like in the first state and the last one, and then you add in the middle as many states as you need. So typically, you only try to do exchanges of coordinates between neighboring replicas because usually non-neighboring replicas would lead to a too low acceptance. The same is true for tempering, whereas here typically you can exchange in a random manner. Okay, let's see. So the method that we're going to discuss today is in this class. So is replica exchange used for tempering your system. So let's also discuss a bit more about this idea of tempering. I would say that the root idea here is the one of simulated annealing. So simulated annealing is a minimization method. So you can use it to find the global minimum of a function with many local minima. And the idea is to simulate at a given temperature and then decrease the temperature during the simulation. So instead of directly minimizing to the closest local minimum, you run at a finite temperature, which means that you are able to overcome barriers, and then you decrease this temperature as the simulation proceeds. And this, if you decrease the temperature slowly enough, can be shown to lead you to the global minimum. So this is a very popular minimization scheme. You can kind of generalize it to be able to sample rather than just minimize. So a minimization is like sampling at temperature equal to 0. If you want to sample at room temperature, say, you should not just cool the system down once, but what you should do is you could have like a list of temperatures that you want to simulate. You would have like room temperature here and a large temperature that is high enough to be able to cross barriers in this graph here. Then your simulation will not just go down as it does in simulated annealing, but will go up and down with a random walk. And then whenever it goes up, your system will be able to hopefully cross some energy barrier and then go down, and it will sample the distribution of interest at room temperature. So this is called simulated tempering. It's not straightforward because in order to make sure your simulation spends the same time on each of these dots, you have to do something iterative. So a very common trick is to use so-called parallel tempering or replica exchange, where you actually simulate simultaneously all these temperatures, and then from time to time you propose an exchange with Monte Carlo, and we will see how. And then if you look at the continuous trajectories, like following the exchanges, what they do basically is a random walk in the temperature space. Okay, so that's the idea of replica exchange. So you have multiple replicas. They are typically simulated at different temperatures. As we will see, you can also simulate them at using different potential energy functions. In both cases, the way you compute the acceptance is this one. So whenever you propose an exchange, you have to compute the probability of the swapped states. So that requires you to know which would be the probability of observing a given set of coordinates in the probability distribution corresponding to the neighboring replica. So, and then you take the ratio between the probability of the swapped states with the probability of the unswapped states. And if the difference between the different probability distributions is just temperature, this can be simplified to this form, where what matters is the difference in energy between the two replicas. If the two replicas, they differ in the potential energy function, so in U, then you have an expression like this one. Or I didn't write it down, but obviously you can write the most general case where replicas differ both in temperature and in the potential energy function. So one important thing to remember is that this is an equilibrium method. So I guess many of you are familiar with metadynamics. That's, for instance, a non-equilibrium method in the sense that you have to adjust your potential on the fly. So you should make sure that you adjust it slowly enough not to drive the system too far from equilibrium. Here, things are different. So here, exchanges are done at equilibrium. So I know people know this, but I try to stress it whenever I talk about replica exchange, because still I think there could be misunderstanding that after an exchange, the system should equilibrate at the new temperature. It should not. So if the exchange is accepted, it means that that set of coordinates is already equilibrated at the other temperature. Okay, good. And in addition, a relevant thing related to this, so is the fact that you don't need to wait many steps between exchanges. And actually, it can be shown that it's a good idea not to wait too much between exchanges. And there's this nice paper here showing this systematically on a set of systems. Basically, the more frequent exchanges are, the better it is. Except for the fact that with the typical implementations, if you exchange too frequently, then maybe the simulation could slow down. And in addition, one should consider that typically decreasing the exchange rate too much so is never a disadvantage, except for this computational cost, but cannot be, it's possible that it's not a big advantage. So typically it's not necessary to use very, very short exchange rates, very, very short exchange paces, but yeah, it's good to choose small strides here. Another important concept that we discussed also in the previous masterclass is that of looking at the continuous trajectories. So here you can imagine all your different replicas, and then if you follow your continuous trajectory, you see that these vehicles are going to be exchanged. So these two are exchanged, and these two are exchanged then. So now if you analyze these horizontal lines, you see that they are at constant temperature. But on the other hand, they contain conformations that come from originally from a separate simulation. So you have jumps in the trajectories. If you analyze one of these trajectories, apparently you have transitions which are very frequent. So it's useful to produce also these so-called the MUX trajectories. I call them like that because the tool in GROMACS to produce them is called the MUX. It's a Perl script, which are continuous. So you can follow them. You can count transitions between state A and B in these trajectories. But on the other hand, the temperature, for instance, in case of parallel tempering, is not constant anymore in these simulations. Okay, good. So now let's go to something more specific of the method that we are going to discuss today. So the idea of parallel tempering is that of increasing the temperature. Now, if you look at how the temperature enters in the probability distribution associated to the canonical ensemble, you see it enters like as a division here, energy divided by kBT. So clearly, doubling the temperature is equivalent to dividing by 2 the energy. And indeed, you could take your force field divided by 2, run a simulation, you will get exactly the same effect as running at a higher temperature by a factor 2. But there's a nice feature of energy. So whereas temperature is an intensive property, so you have one temperature for the whole system, energy is extensive. So if you can like split your system into partly decoupled regions, you could imagine to only scale down the energy of one of the 2 portions and not the energy of the other one. So that would be equivalent in some sense to increasing the temperature only of one of the 2 portions of the system and not of the other one. So why can this be an advantage? So let's say that you have a molecule in water. So we assume that this increased temperature is useful to cross barriers, but we typically do not assume that there are large barriers in water-water interactions. So maybe it's not necessary to increase the temperature of the entire system. If you could find a way to increase the temperature only of your solute, it could be an advantage. And it can be shown, and I will spend a few words more on this in the next slide, that by heating only the solute and heating water, because everything is going to be simulated at the same temperature. So the right wording is by scaling down only the energy of the solute, you can basically obtain a similar enhancing effect with many less replicas. And now I will try to convince you why with some very qualitative argument. But anyway, you can also do the math and see this. So let me make this graph where a point represents like the parameters with which you simulate one of your replicas. And then let's say that you have a system with two coordinates that two subsystems that could be scaled, let's say. So you could decide to scale down by a factor. This would be 1 divided by 0.3. So you would increase the temperature of the horizontal subsystem of subsystem number 1, or you could do it for subsystem number 2, or you could do it for both of them at the same time. Okay, so you see now this is the space of parameters, and if you look at how much you have to travel to bridge between this, which is the reference state of interest, the one not scaled with scaling factor 1 and 1, and this where one of the two was scaled. So look at the length of this and compare it with the length of this. So actually the number of replicas that you need to put here in order to fill this gap is going to be larger here by a factor which is equal to how much longer is the diagonal of the square with respect to the side of the square. That's the square root of 2 because we are in dimensionality 2. If you apply this reasoning to a system with the n degrees of freedom, it will be square root of the number of degrees of freedom. Not all the degrees of freedom of the system, but those that you are actively scaling. So if you manage to scale only, so you know that typically if you have like solvated proteins, typically you have like 90% of the atoms are water. So you can basically obtain the same qualitatively increased temperature of the protein by scaling down only the protein, and this would mean that you typically scale down only 10% of the atoms, and this could allow you to save a number of replicas that could be around factor 3. Okay, so this is the idea of solute tempering that now many people call REST2 for a reason that I will discuss now. So REST is replica exchange solute tempering. The first paper about putting forward this idea of solute tempering, which is named like this because you temper only the solute, is this PNAS paper from the group of Bruce Byrne, 2005. But actually, the same authors later realized that the protocol that they originally proposed was suboptimal. And so they named the second version like REST2. And now this is the version that everyone is using now. So it's very common to hear this name, REST2. So this is the paper describing REST2. So the idea in this paper is to leave water-water interactions unscaled, so at the reference temperature. Protein-protein interaction scaled down by a factor that corresponds to how much you want to increase their effective temperature. And this is the crucial part, protein-water interaction scaled by a factor which is the square root of this factor here. And we will see why this square root factor is not just optimal, but it's also extremely practical. I want to also point you to this paper, which you see is from 2006, which is super nice, I think, and very important, where they propose something very similar, where you have like, you split the potential energy function in 3 portions, say, and one of them scaled with a factor that is fk squared, another with a factor fk. You see, it's the same as here, basically, where fk squared is equal to this ratio. So the very nice idea that is put forward in this paper is that of not limiting this scaling to the full solute, but to select a portion of the solute which is relevant. So for instance, you might have like a large protein with a disordered tail. You want only to sample the disordered tail. Or you have a binding pocket. You want to only scale the binding pocket and the ligand, for instance. It's very flexible method. So why is this square root of lambda the decision to scale interactions between, you see, the hot part and the cold part by a factor which is the square root? So that's very practical. If you look at how the force field is, a typical biomolecular force field is composed, so you have a sum of terms. So in order to make sure that interactions within the hot region are scaled by a factor lambda, so what you should do for Lennard-Jones is to scale this epsilon by a factor lambda. So basically, all the atoms that are located here should have an epsilon which is decreased, so multiplied by a factor lambda. Now, if you look at the standard combination rules for Lennard-Jones, they tell you that epsilon for pairs of atoms should be computed as a geometric average. So automatically, if you don't scale epsilons in the blue region and you scale epsilon by lambda in the hot region, interactions between the blue and the red regions will be scaled by a factor square root of lambda. The same is valid for electrostatic. One could say that the combination rules for electrostatics are again geometrical, because you have a product of charges here. So if you scale all the charges in the hot region by a factor square root of lambda, automatically local interactions here will be scaled by a factor lambda, and interaction between this region and the outer region will be scaled by a factor square root of lambda. What about torsions? Here you have freedom to choose. Clearly, if you apply solute tempering, you could say all the torsions that are part of the hot molecule will be scaled by a factor lambda, and all the other torsions will be scaled by a factor 1. In case you use this partial tempering idea where you scale only a portion of a molecule, you have to decide what to do at the interface. So I think a very practical choice is the one that maintains the consistency between torsional angles and 1,4 interactions. So as you probably know, so whenever you have 4 atoms connected by 3 bonds, so for like pairs like this one, so-called 1,2 pairs, the non-bonded interactions are ignored. For 1,3 pairs, the non-bonded interactions are ignored as well. So basically, there are no Lennard-Jones and electrostatic interactions. For 1,4, you have electrostatic and Lennard-Jones interaction, just scaled down by a factor. And so you have to imagine that these 1,4 atoms are already feeling Lennard-Jones and electrostatic interaction that are scaled down by a factor that is lambda if both atoms are within the hot region, or square root of lambda is one of the atoms is in the hot region and one of the atoms is in the cold region. And so it makes sense to apply the same rule to torsional potentials. On the other hand, for angles and bonds, I think I'm not 100% sure. I guess in the original version they were scaled. In the implementation that I'm using, these are not scaled. Typically, they don't have significant energy barriers, so it's not necessary to scale them. Okay, then a bit more details on the implementation that we are going to use in GROMACS. So the implementation that I added to GROMACS works is very flexible. So it allows you basically to prepare separate topologies for your replicas as you like. But then it has to compute acceptance probabilities correctly. So the practical way that I found to do this, to implement this, is explained in this graph. So basically, so you perform a number of steps of standard MD between one exchange and the next one. Whenever it's time to try an exchange, what you do is you exchange coordinates unconditionally. Then when your coordinates have been moved to the other replica, you compute energy with the force field that has been defined in the other replica, and then you exchange coordinates back. You see, this looks inefficient, and it is kind of inefficient because, for instance, you are moving back coordinates here, which is not necessary. You could have saved a copy here, and similarly, one could, for instance, decide to share the information of the topology at the beginning of the simulation once for all, so that there's no need to move coordinates between processes on the fly. But this was the simplest thing to program, and it actually works, even though it might be slightly inefficient. In any case, this slowing down is only affecting the exchange step, which is something that you typically do every, say, 100 steps or so. Another important technical information about the implementation that we're going to use is that it only recomputes the potential energy. It doesn't recompute the kinetic energy. So velocities are not swapped. Kinetic energy is not recomputed, which means that you should provide topologies with identical masses. Otherwise, the acceptance will not be computed correctly. Okay, this is an example application from this paper where I describe also the implementation. Alanine dipeptide in water. It's actually the same system on which we will play in the exercises. Here you have sampling of phi psi at lambda equal to 1, which is unscaled. And here at lambda equal to 0.3, which is like temperature increased by a factor, effectively increased by a factor 1 divided by 0.3. And you see that as you increase this effective temperature of the peptide, it's more likely to cross barriers. So I would say that alanine dipeptide is not a very good system for this method because there is a very high barrier on a degree of freedom that is easily identified with a collective variable. Still, it makes sense to use it as a test case and to learn how to use the method. And here, similarly, you can see that even in the unmodified replica, you can see multiple times both states, and you can compute the free energy difference. It converges well, and here is a comparison of the free energy profile obtained with the Hamiltonian replica exchange and with metadynamics that works very well for this system. You can just add the potential on phi. Okay, good. So in that paper, there's also an example of this partial tempering idea, which is you only select a portion of a system. So as Max said in the introduction, I like to work on RNA dynamics. So this is just a very simple tetraloop structure. This system is pretty simple, but it's actually known not to be stable with the standard force fields, whereas it is stable in experiment. So here you can see that with a very short simulation, is like 15 nanoseconds per replica. I don't remember how many replicas here. You can highlight the problem. So you can see this is RMSD from native. You can see a significant population of non-native structures mixed with some population of native structures. Here, the simulation was done by restraining these hydrogen bonds and by heating only this portion. This is much more effective than running parallel tempering on the system, which would induce maybe full unfolding and so on. The implementation that you will learn how to use is actually very flexible and can be used also to change temperature and not just potential energy function. And so if you want to have an idea of how to do this from like published papers, you can look at this paper from mine where I was included. So on nanoscale 2017, it's a collaboration with a group of Stefano Corni, where we use this to enhance sampling of a peptide on a gold surface. And also this is a more recent paper on Nature Communications, where we're using a similar protocol to increase temperature at the same time as scaling down energy. So the idea there is when you increase the temperature, you are basically accelerated everything. By scaling down the Hamiltonian, you pick which regions you want to accelerate even more. Another thing that you can do is to combine this method with metadynamics or with methods based on collective variables. We have seen also in the previous masterclass how to combine parallel tempering with metadynamics. You can combine also solute tempering with metadynamics. And I think the first application of this was actually made by Carlo in 2008, although it was using a different implementation, not the one that we are discussing now. So this is the paper where I described the implementation. So hopefully every paper using this implementation should appear in the list of citing papers here. So another thing that you could do is to go here to these citing papers. You can find many reviews, but you can find also many applications, and those could be like examples of advanced application of the methods that we are discussing today. Okay, so now let's go to the technical part. So what you have to do to run these Hamiltonian replica exchange simulations is to first prepare scaled topologies. You can do it by yourself. I know there are around tools to manipulate GROMACS topologies that might be much better than what I'm proposing today. But one thing that you can do is to use this script that is basically distributed as part of PLUMED that can be used to do exactly what we discussed so far. So to scale down a portion of the energy of a system. So what you have to do is, first of all, you have to use this GROMPP minus double P option to create a new top file, a new GROMACS top file that at variance with the original topology file doesn't have any include statement. So usually topology files, they include the force field tables. Here, everything is self-contained. It's a single big file. And now, then you edit this file with a text editor. You just have to select which are the atoms that you want to, for which you want to increase the effective temperature, so scale down the energy. And you just have to add underscores to the names of those atoms. And then you use this script in this example to scale down the energy of those atoms by a factor 0.5 and produce a new top file that can be used directly in a new simulation. So this script, you can imagine, is going to parse the GROMACS top file. It's not guaranteed to always work. You have to double check carefully that it worked correctly. So we will see in the exercises some important tests that you can do. And just to mention one tricky case, C-maps from charm force field are tricky to scale. And if you need to use that on your system, check the PLUMED mailing list. And then, as I said already, you are not limited to this script. You can even use your own tools to generate scale topologies. The only constraint is that the topologies could have different energy terms, but they should all have the same masses, as I said. Okay, once you have prepared your multiple topologies, you have to run. You can run with the replica exchange with GROMACS, and you have to use this multiple replica framework in GROMACS that with current versions only works with multiple directories. So you have to put your topology files in multiple directories. And then since this method is so even if you don't want to use metadynamics or umbrella sampling or a PLUMED input file for anything, you still have to formally include a PLUMED input file. So in most of the exercises, we will use just a simple empty PLUMED input file, or you could decide to use PLUMED on the fly to like print some collective variable for analysis, or you could use a PLUMED file to add some additional biases. So the topologies that you will generate could have different force field parameters. That's what we will do. In theory, so obviously they could start from different coordinates. In theory, you are allowed to use different temperatures. This is kind of test, different pressures, not very much tested. Different lambdas, I think not tested at all. So be careful if you want to. So in theory, all of this should work. So if you want to try these, make some tests. And if you think it doesn't work, just write on the mailing list and we can try to fix. Okay, and then as usual, we'll go to the instructions. So I will now go to the web page, and as usual here we will have the link with the assignments. So let me go now so that we can quickly go through the assignment. So meanwhile, I don't know, any question or comments? No comments, no questions, anything not clear? Okay, so let's see what's the assignment. quickly, and then you will have 1 week to complete it. So the idea here is to learn how to use PLUMED to manipulate topologies and prepare a solid tempering simulation. And then use PLUMED and GROMACS to run replica exchange simulations with multiple topologies. We will learn how to use WAM, so weighted histograms, to combine simulations that were performed with the different topologies. And actually, in the final exercise, we will even learn how to combine replica exchange with metadynamics, so as to properly analyze simulations where the different replicas were subject to different force fields, but also to different enhanced sampling potentials. So as usual, you will find everything in a single repository. Let me check here. Yes, so you have is input file, standard one, standard parameters. We will play with alanine dipeptide in water, so it doesn't make sense to do solid tempering in vacuum because there is no solvent. I was thinking to use some more complicated system, but I realized that even for alanine dipeptide in water, you need significant time to run the exercises. So I think it's better to stay with a simpler system. So here you should find everything that you need, which is initial topology, initial coordinates, and standard set of parameters. And this is a PDB that you can use with the PLUMED to facilitate the analysis, and also a script for WAM that is, I think, identical to the one we used for the other masterclass. So let's see. So here you have some introduction to the method, some explanation about how to run these multi-layer simulations. Very important point, don't forget this -HREX flag. So now this -REPLEX 200 is saying, please try and exchange every 200 steps. If you forget the HREX flag, GROMACS will just think that all the topologies are identical and ignore an important contribution to the acceptance. So the result will be maybe reasonable, appear reasonable, but will be incorrect. So don't do that. Remember to add this option. Okay, so actually exercise 1 as a reference will be a parallel tempering simulation. So no solid tempering yet. So the first point will be try to see what's the effect of changing the temperature on alanine dipeptide. So run multiple simulations at growing temperatures, 300, 400, 1000. You can even go higher if you want. So generate a TPR file and run it. I'm suggesting here 1 nanosecond. So depending on the machine that you use, the performance might vary. So in my cases, I was able to run these 1 nanosecond simulations in something like 10 minutes, which is fine to do all the exercises in maybe a couple of hours. I was using the Conda version of PLUMED, which is quite slow because of GROMACS, actually, because it's compiled with the SSC acceleration only. And it doesn't use AVX, it doesn't use GPU and so on. So if you use your own version of PLUMED and GROMACS, you might have much better performances. Or if you want to play faster, just use shorter trajectories. And then here I suggest to use the driver to compute some torsion angle. You can look at the trajectory of phi and see which is the temperature that you need to use in order to see frequent transitions between the two metastable states of alanine dipeptide. And the definition of frequent is a bit arbitrary and also depends on the length of the simulation that you're going to run here. Then, so this initial test will be used to choose the highest temperature that you will simulate. Will be, say, 1000, 800, 700. Try to take a decision based on the result of these simulations. Then, once you have chosen it, you can run a parallel tempering simulation. Again, this is standard GROMACS. You don't need the PLUMED here. Where the difference between the different topologies is just that they have a different temperature. GROMACS will take care of the acceptance by itself. And you should allocate a ladder of temperatures, let's say between 300 and maybe 1000, let's say. So I would suggest a geometric arrangement, so which would be like uniform spacing in logarithmic scale. If you want, there are web servers to generate optimized distributions. So, and then you can answer this question. So how many replicas you need so that the acceptance between neighboring replicas is at least 30%. And also, if you chose correctly your highest temperature, you will see transitions to the other state also in the lowest temperature replica. So you should be able to compute the population of the both states as a function of temperature. Okay, and now come the solute tempering part. So first thing, prepare these scaled topologies. So you have to generate this process.top file. You have to mark on that file which are the atoms that you want to scale. You see adding an underscore to their name. You can use this partial tempering script to generate a new topology. And you can inspect visually the files or look at the difference to see what's changed and make sure that you understand what the script is doing. There are a few sanity checks that, of course, here they will succeed because this is a simple system. I tested it as well, but they're very important. I would definitely recommend you to run these tests on any new system on which you're interested to apply this method. So the first test is to generate a scale topology which is scaled by a factor 1. So scale by factor 1 means not scaled. Now you can use the original TPR file and the new one, which was scaled by a factor 1, to compute energies from a given trajectory and compare the two energy files that you generate. They should be numerically identical. That's very important to check that the partial tempering script understood correctly all the dihedral terms and so on. A second check that is also very relevant is to make sure that you are really scaling everything, so that when you scale by a factor, you are really scaling everything that you want to scale. So it requires you to first select all the atoms. So in solute tempering, we typically select only solute. Here you will have to select also the atoms belonging to water or ions, if you have ions in your system, or ligands and so on. And then generate a scale topology, which is scaled now by a factor, let's say 0.5. So again, as I said before, so this is not different from raising the temperature by a factor 2. But still, it's useful in testing because you can, again, take the same trajectory, compute energies twice with the original topology and with the new one. In the new topology, the Lennard-Jones, Coulomb, dihedral energy should be scaled down by a factor 2. Angles and bonds should not be scaled. If there is a mismatch, it means that some dihedrals were not scaled, for instance. So these tests are really important, and really I'm stressing that you should do them on any system where you want to run this method. Then there is another test. So basically the test above is a test of this partial tempering script. In addition, you should make sure that on your system, with your settings, the implementation of this -HREX flag is working correctly. I say this because the implementation of this is really tricky, and there might be some setups on which it fails. So really do this test. So this test is just prepare two topologies which are identical. So, or maybe if you want, scale by a factor 1, both of them. And then try to do a replica exchange this way. So if the two topologies are identical, the acceptance rate should be exactly 1. So you can test this and see if the acceptance rate is exactly 1. So why is the acceptance rate exactly 1? What you are doing at every step, you are transferring coordinates to the other processor, recomputing energy there. So if the two processors have read an equivalent TPR file, they will compute the same energy. There are cases, corner cases, where this could fail, but still is a kind of benign failure. So for instance, if you're using GPUs, sometimes the results are not completely reproducible, and so you have an acceptance which is lower than 1. You have to judge case by case. In my experience, this could happen with GPUs, with some like strong optimization, like dynamic load balancing and so on. You could have some acceptance which is slightly lower than 1. That usually is still fine. Okay, and once we are technically able to set up our simulation, we can try to use the method. So before we were finding the minimum temperature required to see transitions. Now we have to find the scaling factor required to see transitions. So I would encourage you to try scaling factor, let's say 1, 0.9, 0.8, down to maybe 0.1. And then run all these simulations for 1 nanosecond and see at which scaling factor you should go to see transitions. As I said, this system is not really, so this method is not very suitable for a system with a large enthalpic barrier. So you will need to go to a very low scaling factor to see transitions. Then you can run Hamiltonian replica exchange simulation. So let's say that you pick as a smallest value for lambda 0.3. You will have to arrange a list of replicas from 0.3 to 1, or maybe from 1 to 0.3. I would suggest a linear scaling instead of geometric empirically, but you can try, you can experiment with this. And also there's an interesting exercise below where we will try to really optimize this ladder. At this stage, a linear scaling would be fine. So check how many replicas you need to put in order to have an acceptance that is at least 30%. The answer, of course, will depend on how low is the minimum lambda you chose. If you chose like 0.7, you will need a given number of replicas. If you chose 0.2, you will need more replicas. And then once you are able to run this replica exchange simulation, you could compute the relative population of the two metastable states, like positive phi and negative phi, at 300 Kelvin. And you could even, sorry, yeah, it's here. You could even run it, you could even do the analysis as a function of lambda. So this is like plotting the population as a function of the temperature quarter, because this is the temperature of only the solute. And it's interesting to compare this trend with the trend that you obtain as a function of the temperature. Next point is combine these simulations with one. So whenever you have multiple replicas methods, you can combine all trajectories and then use one. And here we are using binless one to compute weighting factors for all the frames of the trajectory. So again, the easiest thing is to analyze the reference replica, the one at 300 Kelvin, but you can put all of them together and compute weighting factors. And here you have some guideline. If you learned how to use one already from previous master classes, it's not so different. The main difference is that in this case, the energy will not be produced by PLUMED, but you will have to produce them by using this tool called MDRun minus rerun, which allows you to take a already computed trajectory, and on that trajectory, recompute energies according to different TPR files. This is a difficult exercise. Optimize a replica ladder. You have some guideline here, and I will not give you more input now. Try to read it and try to see if you can do it. Otherwise, we will see next week how to solve it. And finally, the last point is you can go back to this exercise from last year on parallel tempering metadynamics and repeat it using solute tempering metadynamics and see what's the difference. Okay, so that's it. So questions, comments? Is everything clear or everyone is lost? Don't be shy. All clear, great. Okay, so maybe I can ask some question. So how many of you have used this implementation already?
I've used it on alanine dipeptide just to try to recreate the results from the paper you showed.
Okay, good. So
Yeah.
you basically did already the exercises, but
up to a point, right? Up to like some of the new ones that were added. Yeah.
okay, great.
Yeah, but in practice, to try to apply it to my system of interest, which I still haven't gotten to yet. But
yeah, okay. One thing that I forgot to say is that definitely you are encouraged to use this on a different system. If you want to try that before next week we can even discuss together the results. So this method is very useful if you have like a large molecule and you want to only enhance something on a small portion. It should not be difficult to set up, so you're really encouraged to try.
yeah,
Other questions? Yeah.
I'll give that a shot, but I'm definitely going to go through the exercise to talk about it next week, hopefully, since I already have some of it done.
Okay, good. Then other comments or questions?
I have a question.
Yeah.
I was wondering if there are other example of application of your method in PLUMED Nest or realistic system or complicated system or not?
I don't remember actually if there are in PLUMED Nest, but yeah, I think I was doing this. I was thinking to put some work here, but in the end, I did this exercise just before this masterclass. So there are many reviews here, but then there are applications. I mean, the best way to find application, I think, is this one. Look at paper citing this one, because they probably contains a lot of details. So this one by Jan Domansky. There's this paper that I didn't know actually. I was checking it, and they use this implementation, and they have many others. So it's really something that many people are using, and honestly, this is also a bit scary for me because, as I said, so the implementation is very tricky. You have to do a lot of tests to make sure it's working properly on your system. If you look in the code, it's a mess. So the interface between GROMACS and PLUMED is nice. You have like a few key calls to the PLUMED library. To implement this, you have like a part of GROMACS, which is maybe 20 to 30 lines that is copied and pasted in another part of the code with a lot of risk of making mistakes and so on. So there could be corner cases like running on the GPU using the modular simulator, which I don't even remember exactly what it means in GROMACS, or using some other advanced feature that could break down the implementation.
But do you know why the GROMACS developer never implemented a native support for this type of
I can tell you that the day they do it, I will start using that one. And I would encourage everyone to use that one. So one thing that you can do with GROMACS out of the box is to use free energy perturbation. So you know that with lambda free energy perturbation, you can have replicas with scale down of a ligand. For instance, if you want the ligand to disappear and magically reappear in water to compute binding free energies, but you can use this for enhanced sampling as well. You can have the full protein not disappearing completely, it's not necessary, but scaled down by a factor. And that works. I tried it. And there's even a paper from 2011, if I remember correctly, showing how to do that. It's just incredibly slow. Because at every step, my understanding is that GROMACS, so it does like two topologies and then interpolate. So GROMACS computes the energy with both systems and then interpolate. Yeah. It's very slow. That's why I implemented this. So a few years ago, there was a discussion on the GROMACS mailing list, and the GROMACS developer were suggesting to use the PLUMED version, saying that the GROMACS was not yet flexible enough to do this natively. Hopefully things will change at some point and it will be possible to do it without using my code that is very fragile.
Thank you.
Other questions, comments? Okay, good. So then I think we are done. So as I said, so if you want to try this on your system, do it, and then come with questions next week. And yeah, that's it. So bye-bye to everyone and see you next week.
Bye-bye. See you next week.
Thank you. Bye.
Thank you.